we were discussing the measurement of the cosmological parameters, but we stumbled while discussing the cosmic microwave background inhomogeneities and the baryon acoustic oscillations into the field of the evolution of structure. We claimed that we had found in these primordial fluctuations at the time of the last scattering, at the age of 380,000 years after the Big Bang, the seeds of the inhomogeneities we detect in the universe today. Now, once you acknowledge that the universe is not completely homogeneous and isotropic, we are not abandoning the cosmological principle. We are still dealing with a universe that in the large is homogeneous and isotropic, but we are admitting that on small scales there are inhomogeneities, galaxies and clusters, what we actually observe. And the question is two, in fact. And let me address this. I should point out before we start that not only is this going to be a less simple field so that we will be less able to be precise with our simple calculations, it is also a topic that is very much still in development. The theory of structure formation cannot, I think, be said to be a settled field like Keplerian orbits. And so there are ongoing developments, and I will describe what I think I can. So, what do we know? Well, the treatment that, the level at which we understand treating general relativistic cosmology in the presence of a full treatment of an inhomogeneous universe is far too complicated for us. So we tend to separate the problem into two pieces. One is a universe that is by and large homogeneous and isotropic, in which there is a small fluctuation, like the little ripples that we discussed in the context of the baryon acoustic oscillations, and where this fluctuation is small compared to the ambient energy density. In that case, we can make an expansion, think of a almost homogeneous universe with a small fluctuation, and solve the simplified equations that arise from that. At some point, if the fluctuation grows, and certainly a galaxy is not a small perturbation on the vacuum, it is a huge density compared to the average density of the universe, at some point, the fluctuation becomes so large that basically we can ignore, when we're discussing the collapse of the solar nebula, cosmic expansion has nothing to do with it on the scales of the solar nebula. The density, the gravitational interaction, the binding energy in the solar nebula is so much larger than the energies involved in the cosmic expansion that we can neglect the fact that the cosmos is expanding. So we sew together these two solutions, and a typical way to connect them is that once and this is borne out by, in simple cases, we can actually do a relativistic treatment of a suitably symmetric deformation. It's a little technically involved, but it can be done. And one finds that when the variation in density locally is of the order of the mean average density of the universe, then that chunk of the universe decouples from the Hubble flow, stops expanding with the universe, and starts to contract. And from that moment on, you can follow it using sort of Newtonian evolution in a local region, ignoring the Hubble flow. Now, we will assert that once you have obtained a variation in density of order 1 relative to the ambient density, then that will form, depending on the mass that you're looking at, a cluster of galaxies or a supercluster or a galaxy, depending on the fragmentation process, which is sort of understood and is a separate branch, not part of the cosmological approach that we're looking at. Now, initially, if the universe were completely homogeneous at any given time, then of course it would remain completely homogeneous forever. So one has to have some fluctuations, and indeed we see some fluctuations when we look at the cosmic microwave background at the time of decoupling, or at the surface of last scattering. We see that at all scales up to the sound horizon there are fluctuations, and they are of the order of 1 part in 10,000. You will notice that I incorporated the factor of 3 between temperature and density that I gave, and the fact that the temperature variations are a few part in 100,000. The this reflects density fluctuations of the order of 1 part in 10,000. And now there are two questions, or three. One is, if you have a small fluctuation, two things can happen. It can dissipate into the expanding universe, or if the gravitational force inside the denser area overcomes the expansion, then it will begin to contract. Density will continue to increase, and we call those fluctuations growing. If they grow, and if these fluctuations grow and attain order 1 deviation from the average, then we will assert that that is where galaxies form. And our job, of course, since we observe galaxies, is to find a mechanism that allows this to happen. Moreover, it has to happen in the time allotted, because we know when galaxies started forming, or we at least see old galaxies, and we know that galaxies had to have formed by the time we see the oldest pulsars. And the third question, the one we will not answer, is we see these fluctuations. We saw how the fluctuations at decoupling are related to earlier fluctuations at the end of the radiation era by the propagation of acoustic waves in the plasma. But where did those initial fluctuations come from? We will answer that. This is sort of chasing back the flying rubber ball back to the hand that threw it up. We will defer this last question for later and try to address these first two first. And so, what is the question? If you have a given fluctuation, will it dissipate into the expanding universe, or will it grow? And the answer is very related to our old discussion of the Jeans instability. Now, what was the Jeans instability? The Jeans instability asserted that if you have a cloud of gas, say, or nebula, at some temperature and some mass and size, then when the average thermal energy of objects is of the order of the average gravitational potential energy, here m is the mass of the object, r its size, t its temperature, and mu the characteristic mass of a particle in the nebula, say a hydrogen atom. So when these two quantities are of the same order of magnitude, then we said the cloud will collapse, and we use this to estimate things like the temperature of the solar nebula before it collapsed, and so on. And then in a homework problem, we used dimensional analysis to estimate the time it takes for this object to collapse, and the time scale was what we called the Kelvin-Helmholtz time scale. And if you look back at your solutions, dimensional analysis suggested that the time scale, this is time, not temperature, sorry for the notational inconsistency, is of the order of the square root of r cubed over gm. Now we want to write this in terms of density, so we remember that m is up to constants, and we're working to within constants, given by the volume of the object, 4 pi over 3 r cubed, of course everything is spherical, times the density. And so plugging that into here, we see that the constants are irrelevant, r cubes cancel. The time of collapse is proportional to 1 over the square root of g rho. Why am I saying all of this? Because this suggests another way to think of the Jeans criterion. Here's another way to think of the Jeans criterion. Let me clear up my mess. The speed of sound in an ideal gas, which is what we are assuming here, our cloud to be, is on the order, again, there is a factor of order 1 that I'm neglecting here, the ratio of pressure to volume. Taken the square root of the ratio of pressure to volume. If you compute the units, you will see that the ratio of pressure to volume indeed has units of velocity squared. And this turns out to be an estimate for the speed of sound. In an ideal gas, of course, we know that P over rho is K Boltzmann T over mu. We have had a lot of fun playing with that relation in various homework problems and computing average masses and so on. And so I know that we are all familiar with this, so I will replace the speed of sound with root of kBt over mu. And now this gives me another way to think of the Jeans criterion. Notice, if I take the speed of sound in an ideal gas, multiply it by the time of collapse for a cloud that we got from dimensional analysis, I find, well, plugging in, everything's a square root, so I pull a square root out, kBt divided by mu times r cubed divided by gm. And the cool thing here is that if kBt is of the order of gm mu over r, then kBt is gm mu over r. I get a root of r squared here, and I find that of this quantity, the speed of sound times the time of collapse, is of order the radius when the mass of the object is exactly the Jeans mass. Remember, this determines the critical mass at a given temperature and so on. So here's our new way to think of the Jeans instability. An object will be unstable to gravitational collapse if the product of the speed of sound times the time of collapse is of order the size of the object. And this is, for ideal gases, the same Jeans criterion we used before. It turns out, and this would take us beyond the scope of the physics we're doing here, that this in fact generalizes to things that are not ideal gases, such as, say, charged plasmas strongly interacting with radiation. You can define a Jeans radius, r sub j, which is given by the speed of sound times the time to collapse, which is up to factors of 2, 1 over the square root of g times rho. So this expression, it turns out, well, for an ideal gas, it is up to factors of order 1, the same as our old definition of the Jeans mass. And for something that is not an ideal gas, this is the correct way to describe whether it's unstable. Basically, what this is telling you is that the time it takes a sound wave to propagate from one end of the object to the other, or from the center out to the edge, is of the order of the time that gravitational collapse would take. So the object is able to collapse gravitationally in a coherent way. So having motivated, certainly not derived, this expression for the Jeans radius, the smallest size at a given density that a collection of matter with a particular speed of sound will collapse, I can of course just use that to compute the Jeans mass in terms of the density and this object, the Jeans radius. This, it turns out, is the way to extend the calculation to something that is not an ideal gas. You need to use the speed of sound as the bridging gap. Why is this important? Because prior to the decoupling transition, the baryonic matter in the universe was far from being an ideal gas. In fact, it was this tightly dense plasma, strongly interacting with radiation, in which the speed of sound was only 1 over square root 3 times the speed of light. This means, if you compute it, that the Jeans radius for baryonic fluctuations was larger than the horizon radius. And so baryonic fluctuations did not grow. Indeed, we discussed that what happens to fluctuations in the density of baryons during the time before the decoupling era, when we had a dense plasma, was they oscillated. We found a wave behavior. The fluctuation did not sort of exhibit an gravitational instability and grow, but it propagated. Now, if you have a situation where you have a fluctuation larger than the appropriate Jeans radius, but smaller than the horizon size, so that it can still talk to itself, in the context of an expanding universe, if the universe is dust dominated, you find that yes, those fluctuations do grow gravitationally, in the sense that the deviation from average density grows like the 2/3 power of t, coinciding with the growth of the scale factor. And so now we have our information. Imagine that we have these primordial fluctuations with delta rho over rho at the time of decoupling of order 10 to the minus 4. Imagine that these, now that the photons have decoupled, now the speed of sound reduces to its thermal value. Some of these fluctuations are larger than the Jeans mass, and so they can in fact start to collapse, and they will decouple from the Hubble flow when delta rho over rho becomes of order 1, and then they will rapidly undergo gravitational collapse. The time for collapse, as we saw, is rather short on cosmological scales. So, how long will this take? Well, we need to get to delta rho over rho of order 1, starting at t-ionization with delta rho over rho of order 10 to the minus 4. So this will happen at a time relative to T ionization, where T over T ionization to the 2/3 is about 10,000. This is a problem because T ionization is 380,000 years. This leads to a few 100 billion years. These fluctuations, the ones we observe in the cosmic microwave background, are not sufficient to produce. They will grow, they will eventually collapse, but they won't produce galaxies in time. And in fact, in our universe, because of the exponential expansion taking over, all of these dust-dominated approximations will cease to hold. And if these were the fluctuations that we had at decoupling, we would not have galaxies. So clearly something is wrong. In particular, the earliest known quasars extend all the way out, we said, to Z of order 8. And so what we need is, remember that Z, 1 over Z plus 1, in other words, a ninth is A of T. So we have A of T of order 1/9. A at ionization is 1 over 1100. I sort of cheated a little bit. The ratio of A's is the ratio of times to the 2/3 because we're in a dust-dominated universe. This would have required, at ionization, a ratio, a fractional fluctuation. Well, I should have put 9 over 1100, but pretend that we found the oldest quasar at Z equals 7, of order 7 or 8 parts in 1,000, not 1 part in 10,000. We are off by almost 2 orders of magnitude. This is the problem of structure. And the solution to this turns out to be quite interesting. It turns out that in modern cosmological scenarios, we have an understanding of why this is not inconsistent. What is the solution? Well, remember, whatever fluctuations we started with, we will explain why, at the end of the radiation era, the beginning of the matter-dominated era, those included fluctuations both in baryonic matter and in dark matter. Whatever created those primordial fluctuations, the hand that threw up the rubber ball, we will see create fluctuations of similar type in both kinds of dust. However, during the time from the beginning of the matter-dominated era until recombination, baryons behaved very differently from dark matter. Baryons are coupled to radiation. The fluctuations travel and propagate as plasma waves. They do not grow. On the other hand, the velocity of sound in dark matter was low even before decoupling because it was not a tightly bound plasma. The Jeans radius for dark matter was well inside the sound horizon, and fluctuations in dark matter were able to grow as a factor of T to the 2/3 from the end of the radiation era until the decoupling time. And so at decoupling, we have small fluctuations in baryons because they did not grow, but parametrically larger fluctuations in dark matter. These generate then deep potential, gravitational potential wells into which the baryons, once liberated from the photons and able to collapse, as baryonic matter begins to collapse, these collapsing chunks of baryonic matter fall into the gravitational wells produced by the dark matter fluctuations. And it is in this sense that dark matter, the fluctuations in dark matter, seed the structures that we see today in the universe. And again, the detailed calculations are outside the scope of what we are doing here, but it is interesting to watch. This is a recent simulation in which this is a region of, I believe, a few million light year, a few tens of millions of light years on a side. This is a cube of space, a few million, tens of millions of light years on a side, co-moving. So it's a few tens of millions of light years today, and it's expanding with the universe. And in it, what is done is one seeds random fluctuations of the observed magnitude in both dark matter and visible matter, and then lets gravitation take over, and the simulation indicates and shows us that over time, what we see is as Z counts down over here at the top, we see the formation of these filament-like structures, quite reminiscent of the structures that the voids and large-scale structures that we saw in the universe. So, structure formation is a problem. It is not a solved problem. The mathematics is too complicated for us to pursue it in detail. The model of the universe, in which we have a long dust-dominated era, and in which most of the energy density is in the form of dark matter that does not couple to radiation, can produce as solutions to the equations results that are not that dissimilar from what we observe in the universe. This is very encouraging. We think we have the beginnings of an understanding in this concordance model, where all the parameters come together to produce a reasonable answer, where what we observe in the microwave background agrees with what we observe in today's universe, prompting us now to say, well, where did those primordial fluctuations come from? And in general, what happened before the dust era? And we'll turn to what is called the early universe, the more speculative physics in this week's material in the next clip.